Hi, myself Naveen Kumar Saini. In the course Electromagnetic Field Theory, code KEE 301. Today we are going to start transmission line in the unit 5. So, what exactly transmission line is and how it is related with the electromagnetic field theory. So, in the what exactly transmission line is and what is the purpose for that, it is the wave propagation in the unbounded media which we have already used or we have gone through, that is the radio, right, for the TV broadcasting. So, where the information it is being transmitted everywhere, and by who may be interested, that guy can transmit wirelessly. So, in that the wave propagation will not help in a situation like telephone conversation and where the information is being received privately by one person. So, another mean of transporting or transmitting the power or information is guided by the guided structure. Okay. So, two ways are there for transmission of the signal. One is the through the guided way or the unguided way. So, guided structure serve to guide or the propagation of energy from the source to the load. So, in that, so these are the structures for that, where it shows the cross sectional area of the structure through which the transmission line can be used for transmission of the signals. First one is a coaxial line, it is an example coaxial line. Second is two wire line, then C is planar line or the wire above the conducting surface, and then microstrip line. So, these are some of the structures which are used for the as a transmission line. So, in that coaxial transmission line and two wire and the planar line, these are the conventional usable transmission lines in today's scenario. So, they are the transmission line parameters. So, what are the transmission line parameters? First one is the R, this is resistance per unit length. Second is the L, inductance per unit length. G, these are transconductance per unit length, and capacitance per unit length. So, these are not discrete or lumped, but it is distributed in the nature. Okay. So, by this we mean that the parameters that are uniformly distributed along the entire line or the entire length of the line. Okay. So, the all through these parameters, as we said, these are distributed in nature, this will be distributed all over the line. So, for each line the conductors are characterized by these parameters sigma c, mu c, and the epsilon c is equal to epsilon naught. So, these are the parameters for the conducting conductors, right. So, if you remember in the case of in when we discuss about the good conductors in the wave propagation, in that as well we discussed about this, that the sigma c, mu c, and the epsilon c is equal to mu naught are the parameters to define the good conductors. And homogeneous dielectric, which are separating the conductors, which are characterized by the sigma, mu, and epsilon. Okay. So, here some of the properties are that G is not is equal to 1 upon R, where R is the AC resistance per unit length of the conductor which comprising the line, and G is the conductance per unit length. So, this is due to the dielectric medium between the two conductors. Okay. Okay. So, here the transmission line parameters are defined in different transmission lines, in the coaxial line, two wire line, and the planar line. So, in that the four parameters in the transmission line which are defined as are resistance per resistance ohm per meter, inductance, that is Henry per meter, conductance Siemens per meter, and capacitance, that is Farad per meter. Okay. So, these are the results which is gone through the literature, that is also for the coaxial line. Okay. And these are the results which obtained for the two wire line, and these are all the results for the planar line. Okay. So, here the skin depth is one of the parameter for the conductors are defined by this formula 1 upon pi under root of pi f mu c and sigma c. So, these are skin depth of the conductors. Fourth point for the transmission parameter is the value of the L is the external inductance per unit length, okay, above the as we have mentioned in the table, and L is equal to L external. So, the effects of internal inductances, that is L in, which are negligible for the high frequencies. So, at which most of the communication operates. Okay, so these are the formulas for the each line, for each transmission line, that LC is equal to mu epsilon and G upon C is equal to sigma upon epsilon. So, these are the some relations which obtained for the transmission line. For each line is defined by these formulas. Okay, so here it is a cross section of two wire transmission line. Here we said about the inductance and the capacitance and the inductor and the conductance. So, here we see that the resistance and the inductance, these are through the line, right. So, these are distributed through the line, and here here itself there are the two conductors. So, this is a conductor number 1 and this is conductor number 2. So, in each conductor, this conductor is, or each line is has a distributed resistance and the inductance, right. In between these two conductors we have the dielectric. So, in the dielectric, so this dielectric is distributed in nature. So, it is defined by the, it is shunting between for the G and C, right, conductance and the capacitance. So, these are for the dielectrics. So, here when we connect this when we connect the coaxial line with the source, here we see when we connect the source here. So, this source is connected with this transmission line. So, this portion is the source, right, source of the transmission line, and at the other end of the transmission line we are connecting the load. So, this section is the load side and this section is the source side, and this one is the load side of the transmission line. So, when we look from this side, so we see the direction of electric field and the magnetic field is like that. So, when we see from that side, so this cross section is looks like this one. So, when we see from it, then the direction of this direction is the electric field, which is shown here, and this cross section, this section is representing the H, right. So, this is the direction of the magnetic field. So, in the two conductor transmission line, which line supports the TEM wave, right, transverse electromagnetic waves. So, that is in electric and the magnetic field which are on the line which transfers to the direction of the wave propagation, right. So, the significance of that one is when the direction of the wave propagation is in the x direction, then the E or H component will be into the y or z direction as well. So, here we are just analyzing the transmission line. So, for that what we are taking the incremental portion of the length, that is delta z of the two conductor transmission line. So, we intend to find an equivalent circuit that for this line and derive the line equations. In the model of this figure, we assume that the wave is propagating in the plus z direction from the transmission line. Okay. So, we are assuming this, we are using this two conductor transmission line. This is the conductor number 1, this one is the conductor number 2. Here we are using this transmission line in which the E series L, R and L is there, and the G and C is in the shunt nature, on the parallel. So, when we take the cross section here from this one, if we are taking this cross section, okay. So, if we are taking this cross section which is of delta z in nature, so we see that the R and L, because we are representing into the circuit theory. So, in that as we said, the R is what? R is the ohm per meter. So, when we want the resistance section here, so it will be R into delta z. Similar to that, L is the Henry per meter. Here the R was ohm per meter. So, it means this multiplication R and delta z is the ohm and L into delta z is the Henry or the inductance. So, in between we have this G and C. So, this is Siemens per meter and the Farad per meter. So, here when we take the G into delta z, this will become the Siemens, and C into delta Z, it will become the farad in nature. So here when we take this transmission line and delta Z is the length of this cross section. So in that, at the initial phase we have the Z, and at the terminating end we have the Z plus delta Z distance. So we are using the VZT at the input side, and we are getting Vz plus delta Z dot T at the load side. So this is towards the generator and this one is towards the load. So towards the generator means we are connecting the source at the input of the transmission line, and at the load side means we are connecting the load at the other end of the transmission line. Okay. So now we will apply the KVL and KCL into this equation. So here we can see IZT is the input current to it, and in that we are taking delta I here, and I plus delta Z dot T is in another direction. So when we apply the KVL here, then VZT will be equal to R into delta Z into IZT. Okay, and plus here we see L delta Z into del I upon del T, and plus this Vz plus delta T dot comma T. Okay, so this equivalent to this into plus this plus this. Okay, so this is a KVL which we are applying here. So we are just rearranging this equation. So here after rearrangement we are getting this equation that we are taking this one and this one together. So this one is going here. So in this case this is the minus sign, and dividing with the delta Z, this equation will become like this. So we are taking for the particular point, so where the delta Z tends to 0, it leads this equation as the, so this term is equivalent to this one. Okay, del V ZT upon del Z, and that is equal to right hand side. Now we can apply the KCL. So here KCL is what? IZT is equal to delta I plus this one, this quantity. So here we are applying the KCL. Here we applied the KVL. Okay. So when we apply the KCL, then IZT is equal to this one, right? And then what we are doing, we are just writing the equation for delta I. So delta I current will be this current, maybe the I1, delta I1, and this one is delta I2. Okay, so this plus this current into this component and plus this component. So delta I will become G times delta Z, V Z plus delta Z into comma T, and that is C delta Z del V upon del T. So this is the basic thing which you have studied in your network theory about the applying the KVL and KCL into it. So we are applying the KVL KCL onto the distributed section of transmission line. Again we are rearranging this equation. We are taking this one in this side and dividing with the delta Z. So this equation will become like this. So you can say this is the equation number 1, this is equation number 2, and then we have equation number 3, and this will become the equation number 4. Okay. So when we take the delta Z tends to 0, so this equation will become like this. Okay. So we are representing this equation left hand side in this way, in the partial differentiation. This is the definition of the partial differentiation when we take into it. Okay. So what we have this one del V del Z del ZT upon del Z, and here we have the del I upon del T. So in this we are assuming the time harmonics. So as I said, for the time harmonics we multiply with the e to the power j omega t for the time harmonics. Okay, and we take the real part of this equation. So in that what we are doing here, we are just writing we are taking the real part of this equation by multiplying the e to the power j omega t. So this equation will become here we see that R and L. So here we can take R, and in place of del upon del T we can use the j omega. Okay, so when we take the time harmonic, so del upon del T will become the j omega, and we can take I Z T outside. So the equation will become R plus j omega L dot Is. So we are representing I Z T as the Is. and Vzt as the Vs. So we are taking this as the Vs, we are taking this as the Is. So this equation will become dVs upon dz r plus j omega L Is. Similar to this, we will apply the same condition here. So this equation, this will become the Is, this will become the Vs, this is become the Vs, and we are taking del upon del t as the j omega. So when we are doing this, then the equation will become this one. Okay. So very simple. So what you need to do, because we have this equation, this is equation number 5, this is equation number 6. So we will take the we will differentiate this equation, differentiate with respect to z. This equation will become like this, and when you are differentiating, then this term will become del is upon or dis upon dz. So we can put dis upon dz from here, and we can put it into this equation. So when we are doing this, then we are expression which we are getting r plus j omega L into g plus j omega c into Vs. Okay. So as we had defined this propagation constant in the electromagnetic field theory, we are defining the same propagation constant for the transmission line. So this equation r plus j omega L. So here we can say that the gamma square is, we are assuming r plus j omega L into g plus j omega c. Okay. So r gamma square is equal to r plus j omega L and g plus j omega c. So this is the gamma square. So gamma will become what? Gamma will be under root of r plus j omega L and g plus j omega c. I hope this point is clear. So again what we are doing, we are taking the gamma as the alpha plus j beta, sorry. So here alpha gamma is equal to alpha plus j beta, and this is equivalent to this one. Similar to that, we can use this equation. So again the gamma square we are getting, the gamma square is the same, r plus j omega L, g plus j omega c. So when you are solving this equation by using the differential equation, so in that Vsz will be equal to V naught plus e to the power minus gamma z plus V naught minus e to the power gamma z. So this section is representing the wave is propagating in the plus z direction, and this section is representing the wave is propagating in the minus of z direction. Okay. So this is the significance which is mentioned here. Similar to that, for the current equation, I naught plus e to the power gamma z, E naught minus e to the power gamma z. So it is representing the wave propagating in the plus z direction, and here wave is propagating in the minus of z direction. So here the V naught plus V naught minus I naught plus I naught minus, these are wave amplitudes. Plus minus signs are simply representing denote the direction of the travelling of the wave, plus z direction or the minus of z direction. So it is indicating by the arrows, and we obtain the instantaneous expression for the voltage. So instantaneous value for that one is real part Vsz e to the power j omega t. So when we are representing this in the sine and cosine term, then the equation we are taking this Vsz from this equation, and we are taking the real part of this equation. Then the equation which we get for the real part, V naught plus e to the power minus alpha z cosine omega t minus beta z. So here we can write it. So in place of this we can write the real part, that is equal to Vsz is what? V naught plus e to the power minus gamma z, okay, plus V naught minus e to the power gamma z, right, into e to the power j omega t. Fine. So when you are solving this, so what we are getting? We will get real part V naught plus e to the power minus gamma z plus omega t plus V naught minus, we can take it here, plus V naught minus e की power gamma z plus omega t. So when we take the real part, then as we know, when we convert this in the real and imaginary part, we take the cosine this value plus j times sine this value, sine this value. Okay. So in the real part, we will get the cosine term. So here we are taking the cosine term for that, and we are changing this gamma as the alpha plus j beta. Okay, alpha plus j beta. So after rearranging this equation, real part will be real part and imaginary part, and we have to consider that. So real part will be e minus alpha z cosine omega t plus minus beta z, and this is the cosine omega t plus beta z. So this section is representing the wave is propagating the plus z direction. This section is representing the wave is propagating in the minus of z direction. So when the wave is propagating in plus z direction and when it is reflected back in the minus z direction, the standing waves will be generated. Okay, so there is one of the parameter to define that characteristic impedance z naught of the line. It is the ratio of positive travelling voltage wave to the current wave at any point on the line. So in that way, z naught is equivalent to V naught plus upon I naught plus is equal to, with the minus sign, V naught minus upon I naught minus, and this is equivalent to R plus j omega L upon gamma and gamma upon j omega, gamma upon g plus j omega c. So after solving this, what we will get? We will get z naught is equal to R plus j omega L upon g plus j omega c, and that is equivalent to R naught plus j omega N naught. So R naught and Z naught, X naught are the real and imaginary parts of the Z naught. So R naught should not be mistaken by the R, as we know that this R naught unit is ohm and this R unit is ohm per meter. Okay, fine. So the propagation constant gamma. So here we are defining this one as the gamma. Propagation constant gamma and the characteristic impedance Z naught are the important properties of the line. So if we have any of the line, so this line we will define by the gamma and Z naught. Gamma is a propagation constant and Z naught is the intrinsic impedance or the characteristic impedance, sorry. Okay. So when we want the characteristic admittance gamma naught, that is gamma naught is equal to 1 upon Z naught. Okay. And this is the relation, because if you see about the gamma, Z naught and the gamma. So gamma is what? Gamma is nothing but this is the R plus j omega L g plus j omega c, gamma square, and Z naught is R plus j omega L and g plus j omega c. So here we see that in both the parameters gamma and Z, we have all the four transmission line parameters are there. So these are the R, L, G and C. Okay, R, L, G and C. Both the all the four parameters are there in Z naught and all the four parameters are there in the gamma. So that is why the gamma and Z naught are defined to characterize any transmission line. Okay. So one of the special case is the lossless line. So the condition for the lossless line is R is equal to 0 is equal to G. Okay, means R and G is 0. So what is the definition for that? The transmission line is said to be the lossless if the conductors of the line are perfect, means the gamma sigma c is equal to infinite, and the dielectric medium is separating is lossless, that is gamma is equal to 0. So in that transmission line, what is the condition for the lossless line? In that the conductor, we have the perfect conductor, so it means this is tends to infinite, and in between this the dielectric is there. So in that dielectric gamma is equal to 0. Okay. So, the condition for lossless line is R and G is equal to 0. So, in that when we apply this condition R and G is equal to 0 for the lossless line, then the other parameters for using that is gamma alpha, that is equal to 0 when we are solving this. J gamma is equal to J beta is there, and we know about the beta for the lossless line. Beta is equal to omega and root LC. Velocity u is equal to omega upon beta. Okay. So, when we take the omega upon beta from here, then we will get the u, that is the velocity. Okay, that is omega upon beta is equal to 1 upon and root of LC, and that is equivalent to f into lambda. Then we have z naught is 0, z naught is r naught, that is equal to root L upon C. So, this is the case for the lossless transmission line. Similar to that, we have distortionless line. So, in the distortionless line, we have the condition that R upon L is equal to G upon C. So, in that the signal normally consists of a band of frequencies. Wave amplitudes of different frequency components will be attenuated differently in a lossy line as a frequency dependent. So, this results in distortion. So, in that the distortionless line is the one in which the attenuation constant alpha is frequency independent. So, in that the alpha, so this is not the A, this is the alpha. Okay. So, this is the attenuation constant. So, in that alpha is frequency independent, while the phase constant beta is linearly dependent on the frequency. Alpha is frequency independent, but the beta is frequency dependent on the frequency. So, when we apply this condition R upon L is equal to G upon C. So, in that case the gamma which we have, the gamma is what? Gamma we have R plus J, so in that J omega L, and here this is the G plus J omega C. Okay. So, in that we are taking the R and G outside. So, this equation will become this one. So, when we apply the R upon L is equal to G upon C. So, in this equation when we are solving this, then we can just simply put R upon L is equal to G upon C. So, this equation will be, so this will become the square, and it will, we can take it outside. So, when we define this as the alpha plus J beta, so in this case when we compare the real and imaginary part, this is the real part, this is the imaginary part. So, alpha is under root of Rg, beta is omega under root of Lc. So, here we see that alpha does not depend on the frequency, alpha is independent of frequency, whereas the beta, this is a linearly function of the frequency omega. So, alpha is not dependent on the frequency component, there is no frequency component there, and beta is equal to omega and root Lc. Okay. So, beta is linearly dependent on the frequency. So, here when we solve this characteristic impedance, so Z naught we are taking it. So, we are taking the R and G outside. So, in that is 1 plus j omega L upon R, and here 1 plus j omega C upon G. So, so these will cancel out to each other because R upon L is equal to C upon G. Okay. So, here we can use L upon R is equal to C upon G. So, when we use this, then this will cancel out, then what left? R upon G. So, this is the equation which we got for the characteristic impedance Z naught is equal to under root R upon G, and in place of R upon G we can use the L upon C. So, this is the case which we are very much aware, this condition, okay, for the for this case, and we are taking the R naught and J Z naught. So, when we compare with the real and imaginary part, then the resistance will be equal to R upon G or L upon C. X naught is equal to 0, U is equal to omega upon beta, that is equal to 1 upon root of LC, and that is equal to alpha f into lambda. So, these are the parameters which we can calculate for distortionless line or the lossless line by different some conditions. We can then we apply this here. Okay. So, just we have to take care about this equation and just apply the condition for Z naught, R naught and U. So, here the phase velocity is independent of the frequency, we can see under root, this is the J under root LC. So, these are the some of the observations that the phase velocity is independent of frequency because the phase constant beta linearly depends on frequency. So, we have the shape distortion of the signals unless alpha U alpha and U are independent of frequency. Here U and Z naught remain the same as for the lossless line, and lossless line is also a distortionless line, but a distortionless line is not necessarily lossless. Although lossless lines are desirable in power transmission, telephone lines which are required to be distortionless lines. Okay. So, I hope this section is very much clear to all of you, which we have covered about the cross sections of the transmission lines. Different type of transmission lines are existing here, and then we have discussed about different parameters of the transmission lines. Okay. Then we discuss about the equations, voltage and current equation of the transmission line. Then after that we derive this equation and we come to the for some special cases distortionless and the this one lossless transmission line. Okay. So, in the next lecture we will continue from here as well. Thank you very much.